Okay, we are live. Hi, AI and deep learning enthusiasts. It's Saturday. We had some technical difficulties on our regular channel, apparently. I don't know if someone maybe hit like the report button or something and said we were doing copyrighted material, but I got this weird broadcast that said I couldn't live stream from our regular channel. So I created this separate channel really quickly in order to get us started again and just continue today's session. So I just want to reintroduce what we're doing. So this is the AI and Deep Learning Enthusiasts Meetup Group, and we are covering the Deep Learning book, and we are covering the second part of Chapter 12 today. We do have a volunteer presenter with us, and that is Sharif Jazra. Do you want to go ahead and say hi and introduce yourself?
Yes, hi everyone. So I'll just say a few words. I've been a presenter with the Meetup for a few chapters. So my background is wireless technologies. I've been a software engineer in that for 11 years, and machine learning, and then this year in deep learning. So I'm very happy to present. This is part 2 of the chapter on the applications. So I'll get started. Let me just. So we'll restart from the beginning of the section, section 12.4, and so we'll go from there. So all right, so we left off from the section on speech recognition, and now next application is natural language processing. So what is the goal of NLP? It's really the use of human languages by computer. We want to teach computer to use the same language as us. And but there are challenges with the kind of language we use. It's ambiguous. A lot of words have different kinds of meaning depending on their context. And also the language and the syntax defy formal description. So the rules that underlie how words are and sentences are constructed is not definitive, and it keeps changing. One example of an application in NLP is machine translation, where we're translating sentences from one language to another language. A lot of these NLP systems are based on the concept of language model. Basically, they define a probability distribution over a sequence of words, character, or bytes. And given this distribution, we can predict the next word given previous context, previous sequence of words. Early methodology for doing this is n-grams. They're an example of fixed length sequences of tokens used to create a language model. So, so this is a way to capture the probability distribution of a sequence of words. They use probabilities, and in particular the chain rule over a sequence of words. So as a recap for chain rule, we can go through an example of a tau sequence of words, x1 to x tau. By definition, the probability of this sequence can be divided into two terms. A conditional one, the last term x tau condition over tau minus 1 terms, multiplied by the probability of the tau minus 1 sequence of words. And the second term on the right can be further divided in the same way. So it becomes a product of two terms. The first one is the probability of x tau minus 1 conditioned on the tau minus 2 sequence of words, multiplied by the sequence of tau minus 2 words. So we can keep on doing that expansion, and then we reach equation 12.5 in the book, which is given here. So just checking, we have any questions or?
Not yet so far.
Not yet, good, okay. So how do we learn the models, the model for n-gram? We use maximum likelihood. And for this model, it's really easy. The outcome is just counting how many times each possible n-gram occur in the training set. And so we do that for learning the n-gram. So example for n equals 1, this is called a unigram. N equals 2, it's called a bigram. N equals 3, it's a trigram. Gram coming from the Greek meaning something written. So unigram is like something written once. So long history for using n-gram in the literature. we're giving a number of papers here that can be referred to for further study. Typically, when we're training a language model with n-gram, we train both n-grams and n-1 gram, at least. And so this helps us compute the conditional probability for a next word. So this follows the definition of conditional probability that's given here. So the probability of xt conditioned on n previous terms is going to be the ratio of the probability over the n word sequence divided by the probability of the n-1 word sequence. So this is, if you take the denominator and you take it to the left side, you get the chain rule. An example is given. What is the probability of the sentence "the dog ran away"? And using a 3-gram and a 2-gram model. So we'll just use the decomposition here. Note that the first words cannot be used because we don't have on. So we'll have to start with the marginal distribution of 3 words, the dog ran. So we can write this as P3 of the dog ran multiplied by P of away conditioned on dog ran. And then this right term can be further divided into 2 terms, which is by definition the division of the probability of the dog ran away divided by the probability of dog ran. And so the first one, the top one, is a 3-gram. The denominator is a 2-gram model. So it's easy to compute. One problem with n-grams is that many tuples actually may not appear in the training set. So when we compute Pn, Pn-1, we might run into zeros, and that can create either an infinite log likelihood or an undefined ratio. So how do we deal with that problem? One way is to use smoothing, where we are shifting some probability mass to unobserved tuples. So all tuples that are unobserved will have this little tiny probability, and that will be taken away from the rest of the observed sequences. And in theory, that's the same as adding a Dirichlet prior over the count parameters. There are also methods called back-off methods, where you could back off from a higher order n-gram to a lower order n-gram if the higher order one, the sequence in that is not as likely, or it has very 0 or close to 0 values. So then you can try a lower order n-gram. The n-gram is also liable to the curse of dimensionality. So there are, how many sequences are possible here? If the vocabulary is of size v, and there are n-grams, like n possible n sequence of words, then in total there are a combination of v to the power n possible n-grams. So this is a huge number. There's also no good neighbor distance metrics for n-gram. If you're doing this one-hot vector space encoding for a word, and you subtract like a distance between 2 words, you're always going to get the same value, so the same distance. So that encoding is not very good for calculating distances. One improvement mentioned before we get to word embeddings is the using class-based language models. In here, we're basically, instead of using just the words, we're going to combine words into categories. And these categories are calculated based on shared statistical strengths. So we try to partition words using some clustering algorithm, and likely based on the co-occurrence of frequencies with other words, so how often words occur together. The clusters are the categories. And then instead of calculating probability over words, now we'll do probability over the context, which is the category itself. So overall, this reduces the number of needed combinations. However, because we are conditioning on a context, now we also lose information in the process. There were some models that used a mix of word-based and class-based models, and to some extent they were useful. But what the new thing was using neural language model, so language model based on neural networks. To overcome the curse of dimensionality, so let me just make sure. Any questions on n-grams or class-based models?
So far, no questions. I think you're doing great.
Okay, so let's move on with neural language model. So again, to overcome the curse of dimensionality, we can try reducing basically how we encode each word. So we use a distributed representation of words, and that was introduced in Benjo 2001 paper. So here the semantic meaning of word is captured in a low dimensional space. And really it captures relationship between words in that space. This is called word embeddings. In the original space, we talked about the one-hot encoder vector for each word. So two words will have a distance of a fixed distance value, which will be square root 2. While in the embedding space, the distance between the words will be a distance in a smaller but dimensional space, perhaps 100 dimension. And that distance will actually reflect how often the words occur together in the same context. So the distance between words is a reflection of the semantics. This is an example taken from a Badanu paper, which shows the projection of the word embeddings on a 2D space, and then zooming in on particular regions, we find words that are similar, close together. So on the left you see countries close together, and then on the right you see years, dates close together. So that those are different regions of a 2D projection. So how do we deal now with high dimensional output? The problem is, again, we want to predict the next word in a sequence. The next word is, taken from a vocabulary of size V that can be hundreds of thousands of words. And the naive implementation is to just use the softmax as the output. And so when you do that, you have a high memory cost. So you're doing a softmax of xn multiplied by w plus b. W and b are the weights and biases learned. In order to meet that high dimensional output, w will have one dimension, which is the dimension value is v. So w itself will have a large dimension. So it'll take large memory. Also, when we compute the softmax, we have to compute it over all the vocabulary. So it's also high computational cost. So this shows the equation for it. So the y hat below is the output of the softmax function. So it's the denominator we have to sum, we have to normalize. So we have to sum over all the vocabulary. And so that has high computational cost. And also the sum over the weight multiplied by hg in the first equation, that's also done over the whole vocabulary. So one solution was to use what's called a short list. The goal was to limit the vocabulary, the output vocabulary to tens of thousands to 20,000 words. And the way they did it is to split the vocabulary into the short list, the most frequent words that be of size L, and a tail list, much bigger, so but contains also rarer words. So its size will be V minus L. And what we would do here is use an extra sigmoid output unit, which will help us predict whether the next word comes from a short list or from a tail list. And then using that, we can combine two types of models. One that will be applied on the short list words, and one will be applied on the tail list. So the neural language will be chosen for the short list because it has a small number of words, and then we could use n-gram for the rarer words. So this is an example of the probability that we would use. The sigmoid is the probability of I belonging to T, the tail, given the context. So we use 1 minus P and to apply it to our neural language, and we use P to apply the n-gram model. So if the output of the sigmoid is 1, then we will use the n-gram model, and the first term will be 0. And then otherwise we'll use so here in this case the output can be 0 and 1, or it could be a continuous value, so it will just be a mix of the two. The next technique was hierarchical softmax. And so instead of, again, the problem is we don't want to calculate the sum over all the vocabulary terms. I want to find a way to avoid that. In hierarchical softmax, we decompose the probabilities hierarchically into a tree. So this will help us reduce the number of computation from O of V to O of log V. It builds multi-level nested categories of words. So we'll have categories of words and categories, and we'll put those into a balanced tree. So how do we calculate the probability then? For each word, there will be a sequence of decisions along the tree to traverse it and arrive to the word. So the probability of that word then will be the product of the probabilities encountered along the way for each branch. So we'll see that in the next, the image I show next. Here it is. So here we're looking at the probability of the word W4 at the bottom. So what is the probability of W4? We have to see how to get to W4 from the root. First we, this is a binary tree, so there are two decisions, left or right. So B0 here is the decision at the top root, B1 at the second, and B2 at the third level. So at the first level, we have to go right.